Hello viewers of AraaTech, once again presenting a new topic, sequence-to-sequence modeling and artificial intelligence. Let's start the topic. Sequence-to-sequence modeling is an architecture used in artificial intelligence, particularly in natural language processing, where the goal is to transform one sequence into another. It's composed of two main components, an encoder and a decoder. Encoder. The encoder takes an input sequence and processes it into a fixed dimensional context vector, also known as the thought vector or latent representation. This context vector encapsulates the semantic meaning of the input sequence. The encoder can be based on recurrent neural networks (RNNs), long short-term memory networks (LSTMs), gated recurrent units (GRUs), or more recently, transformer-based architectures like the encoder of the transformer model. Decoder. The decoder takes the context vector produced by the encoder and generates an output sequence based on it. The decoder is also typically an RNN, LSTM, GRU, or transformer-based architecture. During training, the decoder is conditioned on the context vector and generates the output sequence one token at a time. At each step, it predicts the next token in the sequence until a special end of sequence token is generated or a maximum length is reached. Training. Sequence-to-sequence models are trained using pairs of input and target sequences. The input sequences are fed into the encoder and the corresponding target sequences are used to train the decoder to produce the correct output sequences. The model is trained to minimize a loss function that measures the discrepancy between the predicted sequences and the target sequences, typically using techniques like teacher forcing or beam search. Inference. During inference, that is when the model is deployed to generate outputs for new input sequences, the encoder-decoder architecture is used similarly to during training. However, instead of using target sequences, the model generates output sequences autoregressively, where the previously generated tokens are fed back into the decoder to generate subsequent tokens until an end of sequence token is generated or a maximum length is reached. Machine translation. Translating text from one language to another. Text summarization. Generating concise summaries of longer texts. Conversation generation. Generating responses in conversational agents and chatbots. Speech recognition and synthesis. Converting speech to text and text to speech. Time series prediction. Predicting future values in time series data. Overall, sequence-to-sequence modeling is a versatile and powerful architecture in artificial intelligence, enabling machines to understand and generate sequences of data, which is crucial in many real-world applications, particularly in natural language understanding and generation. Language translation. Yes, that's correct. Sequence-to-sequence models have been particularly successful in language translation tasks. They have significantly advanced the field of machine translation by providing more accurate and fluent translations between different languages. Here is how sequence-to-sequence models work in the context of language translation. Input sequence. The input sequence is a sentence or a sequence of words in one language, source language such as English. Encoder. The input sequence is passed through the encoder, which processes it word by word or token by token. capturing the semantic meaning of the sentence. The encoder produces a fixed dimensional context vector that represents the input sentence's meaning in a language agnostic manner. Decoder. The context vector produced by the encoder is then passed to the decoder. The decoder generates the output sequence word by word or token by token in the target language, that is French, Spanish, etc. At each step, the decoder predicts the next word in the target language based on the context vector and the previously generated words. Training. Sequence-to-sequence models are trained using parallel corpora, which are pairs of sentences in the source and target languages. During training, the model learns to minimize the discrepancy between the predicted translations and the actual translations in the training data. Inference. During inference, the trained model takes an input sentence in the source language and generates the corresponding translation in the target language. This is done by feeding the input sequence through the encoder and then using the decoder to generate the output sequence token by token. Sequence-to-sequence models have significantly improved the quality of machine translation systems, enabling them to produce more accurate and fluent translation across various language pairs. They have been particularly successful when combined with attention mechanisms, which allow the model to focus on different parts of the input sequence when generating the output sequence. Overall, sequence-to-sequence models have played a crucial role in advancing the state of the art in language translation and making translation services more accessible and effective. Text summarization. Absolutely. Sequence-to-sequence models are also widely used for text summarization tasks where they can condense long documents or articles into shorter summaries while preserving the key information and meaning. There are two main types of text summarization. Extractive summarization. In extractive summarization, the model selects and extracts important sentences or phrases from the input text to form the summary. Sequence-to-sequence models can be trained to rank and select the most relevant sentences or phrases based on their importance scores, which are usually calculated using various features such as sentence position, word frequency, or semantic similarity. Abstractive summarization. In abstractive summarization, the model generates a summary by paraphrasing and rephrasing the content of the input text in a more concise form. Sequence-to-sequence models are particularly well suited for abstractive summarization as they can capture the semantic meaning of the input text and generate human-like summaries using natural language generation techniques. News summarization. Automatically generating summaries of news articles to provide readers with concise overviews of current events. Document summarization. Condensing long documents, reports, or research papers into shorter summaries to help readers quickly grasp the main points and findings. Meeting summarization. Summarizing transcripts or recordings of meetings, discussions, or conferences to provide participants with key takeaways and action items. Email summarization. Generating summaries of long email threads or conversations to help users manage their inbox more efficiently. Sequence-to-sequence models have been shown to produce high-quality summaries that capture the essence of the input text, making them invaluable tools for a wide range of applications requiring text summarization. Conversation generation. Exactly. Sequence-to-sequence models have revolutionized the field of conversational artificial intelligence by enabling chatbots and conversational agents to engage in more natural and human-like interactions with users. Input sequence. The input sequence typically consists of a user query or message such as questions or a statement. Encoder. The input sequence is fed into the encoder, which processes it to capture the semantic meaning and context of the user's message. The encoder produces a fixed dimensional context vector that represents the input sequence. Decoder. The context vector produced by the encoder is passed to the decoder, which generates the response sequence based on it. The decoder generates the response token by token, predicting each token based on the context vector and the previously generated tokens in the response sequence. Training. Sequence-to-sequence models for chatbots and conversational agents are trained on large datasets of conversational pairs, where each pair consists of a user message and the corresponding response. During training, the model learns to generate appropriate responses that are relevant to the input messages. Inference. During inference, the trained model takes a user message as input, generates the corresponding response, and outputs it to the user. This process happens in real time, allowing the chatbot or conversational agent to engage in interactive conversations with users. Sequence-to-sequence models have significantly improved the quality and fluency of responses generated by chatbots and conversational agents, making interactions with them more natural and engaging. By capturing the semantic meaning and context of user messages, these models can generate more relevant and contextually appropriate responses, leading to more satisfying user experiences. Additionally, sequence-to-sequence models can be enhanced with techniques such as attention mechanisms, reinforcement learning, and transfer learning to further improve their performance in conversational artificial intelligence applications. Speech recognition and synthesis. Absolutely. Sequence-to-sequence architectures have been successfully applied to both speech-to-text (STT) and text-to-speech (TTS) systems, playing a crucial role in accurate transcription of spoken language and natural sounding synthesis of speech from text. Speech-to-text (STT) input. The input to an STT system is a speech signal, typically represented as a sequence of audio features, that is, spectrograms. Encoder. The encoder in an STT system processes the input speech signal, capturing its acoustic features and extracting higher level representations of the spoken language. This representation is usually a fixed dimensional context vector. Decoder. The decoder takes the context vector produced by the encoder and generates the corresponding text sequence. At each step, the decoder predicts the next word or character in the transcription until the end of sequence token is reached. Training. STT models are trained on large datasets of audio recordings paired with their corresponding transcriptions. During training, the model learns to map input speech signals to their correct text transcriptions. Applications. STT systems are used in various applications, including virtual assistants, that is Siri, Alexa, dictation software, voice-controlled interfaces, and automatic subtitling. Text-to-speech (TTS) input. The input to a TTS system is a text sequence, typically represented as a sequence of words or phenomena. Encoder. In TTS systems, the encoder is responsible for processing the input text sequence and extracting linguistic features or representations. Unlike in STT, the encoder in TTS may be optional or omitted altogether depending on the architecture used. Decoder. The decoder takes the linguistic representation or directly the text sequence and generates the corresponding speech waveform. The decoder synthesis speech waveform samples one at a time until the end of the sequence is reached. Training. TTS models are trained on paired datasets of text sequences and their corresponding speech waveforms. During training, the model learns to generate speech waveforms that closely match the natural characteristics of human speech. Applications. TTS systems are used in applications such as navigation systems, voice assistants, audiobook narration, accessibility tools for visually impaired individuals, and more. By leveraging sequence-to-sequence architectures, both STT and TTS systems have achieved significant advancements in accuracy, naturalness, and robustness, making them essential technologies in various domains where speech and language processing are involved. Time series prediction. Sequence-to-sequence modeling's versatility extends beyond natural language processing tasks to encompass time series prediction as well. Sequence-to-sequence models can be adapted for time series prediction tasks like weather forecasting, stock price prediction, and demand forecasting. Input sequence. In time series prediction, the input sequence consists of historical data points such as past weather observations, stock prices, or demand levels. Encoder. The encoder processes the input sequence of historical data points, capturing the temporal patterns and dependencies within the data. The encoder typically employs recurrent neural networks (RNNs), long short-term memory networks (LSTMs), or transformer-based architectures to handle sequential data effectively. Decoder. The decoder generates the output sequence of predicted future data points based on the context vector produced by the encoder. Like in other sequence-to-sequence applications, the decoder can utilize recurrent neural networks, LSTMs, or transformer-based architectures to generate the output sequence. Training. Sequence-to-sequence models for time series prediction are trained on historical datasets containing sequences of input-output pairs. During training, the model learns to predict future data points based on past observations, minimizing the discrepancy between the predicted and actual values. Inference. During inference, the trained model takes a sequence of historical data points as input and generates the corresponding sequence of predicted future data points. This enables the model to forecast future trends and patterns in the time series data. Sequence-to-sequence models have shown promise in time series prediction tasks due to their ability to capture long-term dependencies and complex temporal patterns in the data. By leveraging sequence-to-sequence models techniques, researchers and practitioners can develop more accurate and reliable forecasting models for various real-world applications such as weather forecasting, stock price prediction, demand forecasting, energy consumption prediction, and more. Overall, sequence-to-sequence modeling's adaptability makes it a crucial tool in tackling a wide range of artificial intelligence applications, including those involving sequential data like time series.